let's talk about something called weak base ionizations. So we've talked a lot about weak acid ionizations. So remember, ionization is just meaning that something, when it ionizes, it's breaking apart into its ions. Let's just review and kind of compare and contrast the difference between weak acid ionizations and weak base ionizations. So let's just to contrast, say this is what weak acid ionizations look like. Remember, they have this generic formula of the weak acid, HA. So this could be any weak acid, which is aqueous. And water is going to exist in equilibrium with the conjugate acid of water, which is the hydronium ion, aqueous, plus the conjugate base of the weak acid, which is going to be this A-, which is also aqueous. So remember, we always have a conjugate acid-base pair. Here, this would be the weak acid. This would be its conjugate base. Now, the water, because water is, remember, amphiprotic, it can act like an acid or a base. When it's with a weak acid, this would act like a weak base, which would mean the conjugate, this hydronium ion, would be the weak acid. So remember, when we're doing pH calculations, we would use an equilibrium table and the Ka of that specific weak acid to calculate the concentration of hydronium at equilibrium, and then we would use that to solve for the pH. So we've been doing a lot of that, solving for the pH of weak acid ionizations based on initial concentrations of the weak acid and also the Ka of the weak acid. So everything that we're doing now with weak bases is the same, except when we have a weak base ionization, the generic formula looks like this. B, which is going to represent any generic base, plus water, is going to exist in equilibrium. So now, this is my weak base. So now my water is going to act like a weak acid. So now that means we're going to produce the conjugate base of this weak acid water, which is going to be the hydronium ion, plus the conjugate acid of our weak base, which we're going to call HB+. So the acidic proton in the conjugate acid goes in the front, and we would just, this is just the generic conjugate acid of this weak base. So here, this hydroxide ion is the conjugate base of water, and here, this HB+ would be the conjugate acid of whatever that weak base is. Bases tend to be a little more confusing or just less obvious with their structural formulas. So I would always tell you if something is a weak base, you are responsible for knowing the 6 strong acids and the strong acids and the strong bases that we've talked about. So anything that is not a strong base is a weak base. But again, you would also know it was a weak base because it would have a Kb. And Kb's are only for weak bases because they are the weak base ionization constant. So now it's the Kb instead of the Ka. Okay, so let's look at an example. So for this, here's my weak base. This is the general ionization. Again, if I was to draw, well, I should draw this too. Here is the conjugate acid-base pair here and here. Remember, a base is something that is going to accept a hydrogen. So here we are adding a hydrogen ion. That means water acting like an acid is going to lose a hydrogen ion. So just like when we were doing these weak acid ionization calculations, we would use the Ka and the hydronium ion concentration at equilibrium to solve for the pH. That's what we've been doing. So now we are going to use the Kb and the hydroxide ion concentration at equilibrium to solve for pH. So the setup of these calculations work exactly the same, but what you need to remember is that when you're solving for X in an equilibrium table in a weak base, you're solving for the hydroxide ion concentration, not the hydronium ion concentration. So you need to either convert hydroxide to hydronium to solve for pH, or use the negative log of the hydroxide ion concentration to solve for the POH, and then from the POH you could solve for pH. So let's look at an example. So we'll say, what is the pH of a 0.035 molar solution of the weak base aniline? And then you would also be told the Kb of aniline is 4.2 times 10 to the negative 10th at 25 degrees Celsius. Because remember, these equilibrium constants are affected by temperature. So it tells you this is a weak base. So I would not expect you to know what aniline is. You do not need to know the chemical formula for aniline. All you need to know is that aniline is a weak base. So you're just going to use this generic weak base ionization setup to solve for it. And you're given the initial concentration of 0.035 molar, and you're being asked what is the pH, and given the Kb. So let's write this out. So I'm just going to say aniline, I'm going to call it B, plus water is in equilibrium with the hydroxide ion and the conjugate acid of aniline. So there's my reaction, initial, change, equilibrium. So the initial concentration of the weak base aniline was given to us as 0.035. Again, water is not included here because it's a pure substance. We're not starting out with any hydroxide or any of the conjugate acid being produced. So this is minus X plus X plus X, 0.035 minus X, X, X. So now we're just going to solve for X because we are going to use whatever the concentration of hydroxide is at equilibrium to solve for the pH. So over here, I'm going to say Kb, which is 4.2 times 10 to the negative 10th, equals all of this in the equilibrium row, equals X squared over 0.035 minus X. So if I look at my assumption principle, can I assume that this X is negligible? And remember, the way that we do that is we look at the relationship between the initial concentration and the Kb. And if this number is bigger than 500, then we can assume that X is negligible. And here you see that the ratio of initial concentration to the Kb is bigger than 500, which tells me I can assume X is negligible. So I'm just going to get rid of this right here. So now I have 4.2 times 10 to the negative 10th, I'll just rewrite it. 4.2 times 10 to the negative 10th equals x squared over 0.035. So now I'm going to solve for x. I'll just multiply both sides by 0.035. And then I'll take the square root of both sides. And when I do that, I'll be left with x. And when you do that, so 4.2 times 10 to the negative 10th times 0.035 square root is, with two significant figures, because my initial concentration has two significant figures, x equals 3.8 times 10 to the negative 6th. So remember what x is. X is the hydroxide ion concentration, not the hydronium ion concentration. A lot of people will forget to do this step when they are solving these problems because they've just been in the habit of doing weak acids. When you're doing a weak base, remember what X is. X is hydroxide in this case. So I can use the hydroxide ion concentration at equilibrium to solve for the pH. Two ways. I'm going to do it two ways just to show you. So first, let's say we are going to use the hydroxide ion concentration to solve for the hydronium ion concentration. We'll do it that way. And then we'll also use the hydroxide ion concentration to solve for the POH and then solve for the pH that way. So we'll see that we're going to get the same answer with the correct number of significant figures. Okay, so here I'm going to say the kW of water is 1.0 times 10 to the negative 14th, which is the hydronium ion concentration times the hydroxide ion concentration. So 1.0 times 10 to the negative 14th equals the hydronium ion concentration times 3.8 times 10 to the negative 6th. So if I divide both sides by 3.8 times 10 to the negative 6th, you should get 2.6 times 10 to the negative 9th. So hydronium ion concentration equals 2.6 times 10 to the negative 9th molar. And then from that, we can solve for pH. We can say pH equals the negative log of the hydronium ion concentration, 2.6 times 10 to the negative 9th. pH equals 8.58. Remember the number of significant figures in the concentration. Two significant figures are the number of decimal places in the pH. So it's 8.58. So now let's do it the other way. We're going to use the hydroxide ion concentration to solve for the POH. So I'm going to say POH equals the negative log of the hydroxide ion concentration. POH equals the negative log of 3.8 times 10 to the negative 6th. POH equals 5.42. I know that 14 is the sum of the pH plus the POH. So if I say 14 equals pH plus 5.42, and I subtract 5.42 from both sides, then I have pH equals 8.58. Technically, you would say 14.00 here. The number of significant figures in your final answer comes from the number of significant figures in the problem. If the concentration has two significant figures, the pH must have two decimal places. Something else that you should always be thinking about, because it is easy to get in the habit of doing these calculations without really thinking what the numbers are meaning. This is a weak base, ionization. So think about bases. We know that bases have a pH that is greater than 7. If you are doing a weak base ionization and you get a number that is less than 7, that is an acidic pH. That doesn't make any sense. Here we did a weak base ionization and we got numbers that were greater than 7. This makes sense. This would just be a good way to check that you didn't accidentally set up your problem wrong or make a calculation error somewhere along the way. Think about what the calculation is trying to tell you. This is a base ionization, which means it should give you a basic pH.